Welcome back to part 3 of this chapter. So it's also interesting to look at two bond coupling constants. So what we're talking about typically here is the coupling between a proton and another proton mediated by two bonds attached, for example, to a common carbon. And in the case here, if we look at the proton-proton coupling between these two protons attached to the same carbon, because the molecule is, these protons are not equivalent, it turns out that we have unequal, that we can measure this coupling between them. And these couplings, as you see, are on the vicinity of a few hertz, and they are critically dependent on the question if the substituent X here, if it's an electron donating or withdrawing group. And in this case, the dependence is even more pronounced. We see here, this is a coupling between two of the protons attached to the same carbon, and this is X, and now we're talking about this coupling here. And it turns out that these couplings are generally negative, and they are in the vicinity of -10 to -17 hertz. Incidentally, you may not have heard of negative couplings before. Very often in the literature, NMR literature, nobody mentions the sign of the coupling, and what people actually report is simply the absolute value of the coupling. And of course, if you do it that way, you cannot see the sign. The fact is that it is rather tricky to determine the sign, and it takes a bit of understanding of NMR, and particularly of two-dimensional spectroscopy or multiple resonance, in order to detect the sign. But signs have been measured and can certainly be calculated. Now, some people have been looking for very exotic couplings so that they have a chance to get a record in the Guinness Book. And here, for example, we have a very long-range coupling between two protons separated by 1, 2, 3, 4, 5 bonds. And because of the delocalized structure of the electrons, this is about 2.2 hertz. Mind you, all units in this chapter are given in hertz. And we can even go to 7 bonds, and it turns out that we then have a negative coupling, rather strangely. You may wonder how one can measure this, because these two protons are magnetically equivalent. Well, there is no multiplet structure, but what you do is you replace one of them by a deuteron, and then of course it becomes inequivalent, and you have a long-range J coupling, and in this case you can see that JHH is proportional to JHD, provided we multiply it by the ratio of gamma H over gamma D. So we measured HD in an asymmetric molecule and then apply this rule in order to draw a conclusion about the HH coupling. More straightforward is in benzene groups. It turns out that orthocouplings between neighboring protons, so this is an orthocoupling of course, is somewhere between 7 and 10 hertz depending on the substituents. Metacouplings are smaller, and paracouplings are typically on the order of less than a hertz. So this is smaller and this is almost negligible because they can be detected. Likewise, if we have molecules that are rigid, this doesn't work if they are floppy, but if they are rigid, then we can have long-range couplings, provided the arrangement of the bonds is in a so-called W structure that allows one to convey the information through the electrons. There's some interesting properties of J coupling constants that are worth knowing. Some people have an encyclopedic knowledge about these things. First of all, one can distinguish between proton-proton couplings that are on the cis, on the same side of the double bond, or trans, so cis and trans. And these couplings, as you can see, the cis are in the vicinity of 10 and the trans in the vicinity 15 to 19. And they critically depend on the question whether there is a substituent here in the third position. So many people, good chemists, can know these things by heart, and just from the knowledge of the coupling constants they can tell you what the substituent X really is. There are other examples here. So this is now the proton-proton coupling between these protons here, that is to say between vicinal protons, and they are in a smaller, contained in a smaller range, but also depend on the substituent X. This kind of observations is very important in chemistry of cyclohexanes and their derivatives, and in particular of sugars, because many sugar molecules are built on the six-membered rings with an oxygen and of course hydroxy groups, but the basic pattern is a six-membered ring. And it turns out that here we can distinguish axial coupling. So if there's a proton up here and a proton down here, then this is an axial-axial coupling, and that turns out to be has a dihedral angle, if you look at the Newman diagram, of 180 degree, and the scalar coupling is quite large, in the vicinity of 12 Hertz. But if we now consider, for example, between this equatorial proton here and this axial here, so now there is a 60 degree dihedral angle, and the coupling drops to about 4 Hertz. And likewise between the two equatorials, so if we compare this and this, there is also coupling between those two. Again, the dihedral angle, although that's not obvious from this diagram, is only 60 degrees, and the coupling is 3.9. So there are important lessons to be gained from looking at 3-bond coupling constants. Now, of course, this hasn't escaped the attention of some theoreticians, and there is a famous relation that was invented many years ago by Martin Couplings. He got a Nobel Prize a few years ago, but that was not for this equation. But his equation explains a relationship. It's actually partly empirical, partly theoretical relationship, of which Couplings himself said that if you use it, is it at your own risk. But anyway, I won't give the equation here. But the point is that the J coupling between two protons in vicinal positions are dependent on the intermediate dihedral angle. And in fact, this J coupling is largest if the angle is 180 degree, that is to say if one proton is sitting here and the other one is sitting there. They are somewhat smaller, but not dramatically smaller if the angle is 0, that is to say if the two protons are eclipsed, that is if the back proton is hidden behind the front proton, so to speak. And they drop to something like 2 degrees or so if the angle is 90 degree, which it frequently is. Such relationships can again be calculated using quantum chemistry, but they can also be observed in molecules, provided that you fix the angle, you contrive the molecule with suitable substituents and rings and what have you, in order to prevent it from rotating. Couplings postulated a famous equation which bears his name, and it says that a 3-bond coupling is proportional to a constant plus a factor b times cos theta, which is the dihedral angle, plus a factor c, parameter c, times cos square theta. So you see that if the limit that theta is equal to 90 degree, then of course cos and cos square disappear, so J3 becomes equal to A, and in the limit that theta is equal to 180 degree, then the cosine is -1, the cosine square is +1, so the 3j then says we have A minus B plus C, and of course the limit that the angle tends to 0 is 3j equal A plus B plus C. So basically this Couplings equation is a nice way of empirically catching that complexity. And we see such things if we look at amino acids. An amino acid can be represented in a Newman projection. So in front here we have what's known as the alpha carbon, which sustains or is attached to the carboxy group and the ammonium group of the amino acid. And then behind it, behind the disk of Mr. Newman, is the beta carbon. And on that beta carbon we find the residue, the rest of the chain, plus a beta 2 and a beta 1 proton. And on the alpha carbon, of course, we have the alpha proton. And so the question is, what is the coupling between these two and what is the coupling between these two? And it turns out that depending on the angle theta, which is the angle through which these two planes are rotated, that these couplings vary dramatically. For example, in this configuration we have between alpha and beta 1 we have about 60 degrees, and between alpha and beta 2 we have 180, and in this configuration this is about 60 and this is about 180. So you see that the coupling will vary depending on the angle theta, and on average we shall be observing the weighted average of these three couplings, and therefore we can draw conclusions as to the value, the average value of this angle theta. In fact, this is a rather modern subject. We find similar things in polypeptide chains, that is to say a chain of amino acids, but in a slightly different disguise. Here we see there are couplings between the proton attached to the alpha and the proton attached to the nitrogen, which is part of the amide bond. And here there is a coupling, so this is a 3J H attached to proton and H alpha, will tell you about the dihedral angle here, which in the language of peptides is known as the angle phi, the other one being psi and chi. Well, this kind of the knowledge of these couplings, which can be determined even in fairly large molecules, allows you to determine that angle. And if you know such angles from one peptide bond to the next, ultimately you can define the entire three-dimensional structure of the peptide, and that is a very flashy thing to do. Now, in this chapter 3 of Peter Hall's book, there is also a brief discussion of dipolar couplings. Now, dipolar couplings do not occur in liquids, as we shall see, but they occur in solids and are very important as such. And they can be seen in solids in the form of splittings, but they also influence spectra in liquids because they are essential to drive relaxation. Relaxation, as we shall see, is a process through which the magnetization returns to its thermal equilibrium, and as such it's very important both to be able to record NMR spectra, but also to determine certain molecular properties such as internal motion or diffusion coefficients, rotational and translational diffusion. So dipolar couplings are on a different type of thing. So what you see here is doublets of a spin A coupled to a spin X in a solid as a function of the orientation. So the reason for these splittings is that we have a spin A, so somewhere here, let's call this spin A, and then somewhere else in space there's another spin, let's call it spin X, and they together subtend, or their interaction, their distance is described by a vector. And this vector this molecule will be placed in an external magnetic field, which we call B0 as usual. And if we extend this internuclear vector, we find an angle here that defines this as the angle called theta. And it turns out that the energy level diagram is affected by the dipole-dipole couplings. So this has nothing to do with the J couplings, it has nothing to do with electrons, it is purely mediated through space. And you see here that there is an angular dependence. In fact, this thing is called as the Legendre polynomial of rank 2, sometimes called just P2. And the peculiar property is that it depends on the orientation of this vector with respect to the magnetic field. And so you give an example here of the doublet of this. This is split into a doublet, so it's a large doublet if theta is 0, that is to say if this vector is aligned with the magnetic field. Then there comes a point that it goes through 0, the doublet collapses to a singlet. That turns out to be the case when theta is equal to about 54 degrees, which is the so-called magic angle. And if that is the case, we only have a singlet, and then the splitting reappears, and as we go to 90 degrees, as to say if this vector is perpendicular to the external field, we have a splitting which in magnitude is 1/2 the splitting that we have if it's parallel. It turns out that this splitting, which the authors call R, rather untypically, most other journals, other books call this D, but it's proportional to the product of the gyromagnetic ratios of spin A and of spin X, and most importantly it's inversely proportional to the third power of the distance between them. So R in this case is simply the length, the modulus of the vector that we have drawn here. And that vector R, that distance R, of course is interesting to chemists because it allows you to measure the size of a molecule and the length, the distance between two spins. Now it turns out that if we consider powder, then there is no single orientation of this vector R. So let me draw the field again. and remember that we have an internuclear vector like this which subtends an angle theta. If we have a powder, that means that we have all sorts of particles, a bit like in sugar or in salt, that have different angles, and consequently theta is distributed over a full range of angles. And it turns out that we then get a powder spectrum, also invented by George Pick, by the way, in the 50s, discovered for the first time and explained, that's more importantly. And it turns out that the small splitting here, RAX, which is on the previous transparency, corresponds to the case where theta is exactly equal to 90 degrees, and those crystallites are fairly common because it's quite likely that the vector be perpendicular to the external field. But this larger splitting here corresponds to theta equal 0 or 180 degree, and the signals are weaker here in amplitude because the likelihood that they should be precisely parallel to the magnetic field is much smaller. In fact, you can see that this Pick pattern is made up of two halves. It's actually a superposition of two parts like this, and these are the two transitions of the two spins of the doublets that we're talking about. Now let's recapitulate together with Peter Hoare what is to be said about J-couplings and dipolar couplings. First of all, J-couplings require bonds. They are mediated by electrons. If there are no bonds, there are no J-couplings, whereas dipolar couplings go directly through space and therefore can be intermolecular, for example, whereas these can only intramolecular. J-couplings are weak, typically on the order of 100 Hertz or something like that. Of course, there are some exceptions, but that's an order of magnitude. And dipolar couplings tend to be much larger. It depends on the gamma of the nuclei, but 100 kilohertz is a good number. J-couplings are isotropic. That means, in fact, that is what scalar coupling means. Isotropic in the sense that their magnitude is independent of the orientation of the molecule with respect to the magnetic field. And dipolar couplings vary with the orientation according to the Legendre polynomial, that is 3 cos square theta minus 1, where theta is the angle subtended between the magnetic field on the one hand and the internuclear vector on the other. Then J-couplings tend to drop to small numbers if there are more than 3 bonds that separate the nuclei, whereas dipolar couplings always are proportional to the inverse of the third power and therefore insensitive. J-couplings cause splittings in spectra in solution, where they also can be seen in solids, but that's more difficult because they're so small, whereas dipolar couplings lead to splittings, large splittings, in solids and also in more exotic things like liquid crystals, such as partially aligned molecules. J-couplings do not contribute significantly to relaxation, that is the return of the magnetization to its equilibrium, but dipolar couplings are causing relaxation. In fact, they are driving relaxation, particularly in the presence of motion, and therefore they give a way of determining this motion. There are some comments here. The strength of the interactions, both this and this, depend on the magnetogyric ratios. I call them gyromagnetic, but that's the same thing, and on the molecular structure. The numbers are very approximate, so this is just to guide the eye. They can be more complicated if there is chemical exchange going on, and one has to worry about internal motion. So, in summary, spin-spin interactions, they can be either J-couplings in liquids or dipolar couplings in solids, give rise to multiplets. So in liquid state spectra it's only J-couplings, and in solid state spectra it's mostly dipolar couplings. J-couplings usually occur via chemical bonds because they are mediated by electrons and are generally small when the nuclei are more than 3 bonds apart. J-couplings give information on bonding networks in molecules. Now, J-couplings within a group of magnetically equivalent spins do not produce any multiplet splittings. So as soon as you have identified an ensemble of spins that are magnetically equivalent, there's no evidence that there are couplings between these spins. Strongly coupled spins have more complex spectra than weakly coupled spins, and particularly when we have a 2-spin system, the inner lines tend to grow at the expense of the outer lines, and this is known as the roof effect, and in larger spin systems they can be very, very complicated. Dipolar couplings occur through space, normally do not lead to multiplets in liquid state NMR spectra unless we happen to be in materials or in molecules, liquid crystals that are partly aligned with respect to the magnetic field, but this is clearly a very exotic subject. Thank you for your attention.